Okay. No, we want this one, don't we? Okay, so we're live. Welcome, everybody. Welcome wherever you are around the world.
So, how are you all doing? Have we all done the paper?
We've looked through it, yeah.
Okay. So, if you have any question about what I'm saying, just drop in.
Alan is studying maths at Emmanuel College in Cambridge. He's really good at sums, aren't you? Hard sums in particular. No pressure.
So, for question one, we can see that straight away there are two unknowns or variables we're looking for: the tension and the acceleration. So, the thing about tension is that when you're looking at how the tension is acting on the object, we typically have a string, and tension is always starting from the object and pointing along the string. So the resultant force will come this way. And when you're drawing...
This is connected in case you want to use the graphics pad. It might be. It should be. Yeah. That's it. It might be a little bit better. And you've got an eraser there, Joe. That arrow's fine. Just, yep.
So this is meant to be a straight line. It will come from the object pointing along the string.
If you want to, you can do the straight lines from the straight line tool, which is
this one.
No, left, right a bit, right a bit. It looks like circles and squares.
Oh, right.
If you click there, and then on the right hand side you've got like an arrow tool, so you can use that. Yeah. That's it. Oh, perfect.
And one of the things about tension is that the magnitude is always the same. Maybe the direction is different, but why is the magnitude always the same? Because as we see in the question, the string is itself light. Let's imagine a situation where the tension is not the same along the string.
Let's go back to the rub. That's it.
Yeah, there you go. So I have a piece of light string. So light just means its mass is negligible.
Yeah.
If the tension here, let's call it point A, it's not the same as tension here, point B. Let's suppose the tension at A is slightly larger than at B. Then let's consider this little piece of string. It has effectively zero mass, but a non-zero resultant force, which means it will accelerate to infinity. And that's not a physical situation, so the tension must remain the same.
So, and the key word in the exam for this is inextensible, isn't it?
Light and
inextensible.
Inextensible means there's no extension and there's no elastic energy stored in the string. There might be some situation where there will be, and there'll probably be in M2.
Yeah. So the key words you're looking for: light, inextensible, and that just means that the tension is the same all the way on the string. Brilliant.
Exactly. And so yeah, straight away, because we have two unknowns and some.
What do you need, son? Yeah, that's it. Just click one more time. Yeah.
So I have two unknowns. Tension and acceleration.
It'll auto-correct, hopefully. Yeah, there you go.
Okay. And so we have two equation here. We can hopefully set. So what's the what other forces are there on the object Q apart from the tension?
Gravity. Yeah.
So yeah, we'll have gravity acting downwards. And which of Newton's law should we use for acceleration, relating acceleration to forces? Second, yeah. So we have second law.
And that code, for people that don't know, is N2, means Newton's second law. That's it. Good.
How does Newton's second law apply to object Q? So we have tension, and we have what's the force acting downwards? That would be 0.4 times the g, the constant of gravitational acceleration, minus t, that will be the resultant force. And what's that equal to? Force equal to, so let's just revise Newton's second law. It simply states that the resultant force on an object is equal to its mass times acceleration. And the mass of Q is 0.4. And acceleration is a, which is, again, an unknown. So we have one equation and two unknowns, which is obviously not enough. But we have another equation which coming from the object P. So the first equation is coming from applying Newton's second law to the object Q. And what's the forces acting on the object P? There's only one force acting on object P. That is the tension acting along the string. Again, T. So what's the resultant force is simply just T equals 0.6a. So again, on the left-hand side, have the resultant force, and on the right-hand side, have acceleration.
Now, one thing you might want to cover, Alan, is why is the A the same? How do we know the acceleration is the same?
Okay, so why it's the same is because A, the string is inextensible, so they must be moving at the same speed. And another thing is there's no reason for P to be moving faster than Q, because the only force providing the acceleration is the tension. And the tension is coming from the fact that Q is moving downwards. So therefore, Q and P must be moving at the same speed. So another approach might be looking at the system and say, okay, we have P and Q connected together. Let's treat them as one object instead of two. And the only resultant force is the gravity acting on Q. So we could just say that A equals 0.4 G over 0.6 plus 0.4. But that's another approach. Let's finish with the Newton's second law approach first. And then solving this simultaneous equation, we'll see that we get the same answer, A equals 0.4 G, which is, in this case, 4 meters per second square. And from...
In your formula booklet, you're told to take G as 10.
Yeah.
10 newtons per kilogram. Yeah.
So that's that. And then from, because T equals 0.6a, so T equals 2.4 Newton. Any questions?
Let's see the whole thing. Okay, nice one. Did you get that one more or less? That one?
Yeah, yeah, I mean, the main thing that saw me originally is I didn't understand that G was 10. And I kind of stuck there. But.
Okay, I think, so for this example, just take G as 10.
Yeah, correct. Yeah. I think you may be told that at the beginning of the paper as well, maybe. Not sure. Okay, cool. Crack on. Do you want to go down to number 2? Yeah, that's it.
Okay.
Perfect. Now, one confession, when I rearrange these PDFs to put spaces in, the degree sign disappears and it turns into angstrom units. Yeah, I know. So whenever you see 20, funny thing, that just means degrees. So that's just on this version, because I tried to create some spaces in, so when Alan writes, you can actually see the solution and the question together. Okay.
Right. So question 2. We have a particle resting on an inclined plane at 20 degree. So in this kind of question where it's not in a horizontal kind of frame, we have to be careful as to how we resolve forces. Because we know the force that's causing all the motion is obviously gravity. But we'll have to resolve it into horizontal and vertical components. In this case, vertical to the plane and horizontal as in parallel to the plane. So what's the angle here? Let's try to draw a bigger diagram. So gravity is acting perpendicularly downwards, and it is 20. So what is this angle here?
What does that second line represent?
Oh, so this line is just perpendicular to the ground.
Have a guess.
20?
Yeah, it's 20 because how do we know it's 20? Because this angle plus this angle must be 90, and this small angle plus this small angle must be 90, so this angle must be 20 as well. So we know that the force normal to the ground is just mg cos 20. And this is true in any kind of situation. All we need to change is the angle. So this is sometimes as we call the normal force. But as we can see that the force acting perpendicular into the floor is perpendicular to the line of motion, so it's not doing any work. That's not the force that's causing the motion. The component that's causing the motion is the component that's parallel to the ground. So that's the parallel component, which is mg sine 20. Okay. So in this case, we are told that the magnitude of the frictional force is constant, because that's one of the things that we assume, and obviously gravity is constant. So we know that the acceleration of the particle is constant. So when we have constant acceleration, we know the initial speed and the final speed. So A would just be V minus U over T. This is just a application of Suvat, and that will give you 0.4. So we know the acceleration. How do we find out the magnitude of the frictional force?
Any ideas, guys? It's the same general idea as what happened earlier on.
So when we're concerned with some force and acceleration, always think back to Newton's second law, because that's the most fundamental rule that relate force and acceleration.
What was that Newton's second law from earlier? Remember how it was written?
Force equals mass and acceleration.
That's it.
Okay. So what are the forces acting on this little particle?
Oh, that's not a prop. You want to? You can just select it all without the click on the eraser again. Yeah, and then just drag around all of whatever you want to delete or move. You can sort of drag around it. So, yeah, you can delete it all. Yeah. So. Then go back.
So let's imagine this particle still lying on the inclined plane. So we know that one of the forces that's acting on them is the component of gravity parallel to the plane, and that's g sine 20. What other forces are hindering the motion?
What forces are hindering it?
Yeah.
Friction.
Frictional force. Let's call it F. So in this direction, the resultant force is that minus F, and that will equal to. Let's look back to the second law here. So what would this be equal to? What's the mass of the particle?
That's it.
So that will be 0.1. And acceleration, as we've just worked out, is 0.4. And because we know m, we know g, and we can use our calculator to work out sine 20, we can immediately work out f to be 0.302 n. And this is 3 significant figures. So again, most of the early questions, all you need to do is remember Newton's second law. Did you all get that in your question?
Yeah, I mean it's just the first day of it, so you don't have to worry too much about just crack on to it and see how you go.
Okay, and coefficient of friction. Does anyone know what that is? Let's denote mu. So what is the coefficient of friction? So normally, let's denote, it's just the ratio between the normal force and the frictional force and the normal force. So that is be our particle. The normal force is just the component of the force perpendicular to the plane, R. And because of this normal force, there will be a friction, F, and the coefficient of friction is simply the ratio of them. So what's the component perpendicular to the plane? We've said before is mg cos 20, and that's the normal force, and the friction force is F, so mu is just the ratio between the frictional force and the normal force. Any questions?
Cool.
Question 3. So we've now kind of moved on from Newton's laws of motion to another set of equations governing motions with constant acceleration. How do we know acceleration is constant? Because any motion that's occurring without friction and kind of under gravity, we can assume to have constant acceleration, and then we can use Suvat.
You might need to explain what Suvat is very briefly because they won't know that.
Okay, so
they get those in the formula booklet, don't they? I think.
no, let's just start from scratch.
Okay. Yeah.
Suvat is just a acronym of the 5 most important components of a anything that's in motion. So S stands for displacement, and U normally stands for initial velocity. V stands for final velocity. A is just acceleration. And T is time. And the first equation of relating sum of the quantity is just V equals U plus AT. This is very easy to understand because it's just saying that when you have a constant acceleration, the final velocity is the initial velocity plus acceleration times time. That is just the definition of velocity and acceleration. And the second step, it's a little bit harder. It's displacement equals ut plus the half at squared. This is slightly harder to interpret, but a heuristic approach would be to draw a graph.
Maybe use the lines.
Yeah.
Let's see how that works. The next one, that's it. Yeah, either arrows or that's it. Fine. And you can move it into position. Yeah, perfect.
This is a velocity against time graph. In a velocity against time graph, the important thing to remember is that the distance is simply the area under the graph. So here we have U, and here we have V. And how do we work out the area under the graph, assuming this is a straight line? So first we have just a good old triangle, rectangle here. So it's just UT. And then we have this triangle here. And the length of this side is just a change in velocity. So that's AT. And so the length of this side is again T. So the area will be a half AT times T. So it's AT squared. Another way you can derive this result is just by integration. Don't know if you guys have done integration.
No.
Well, you can come back to it later if you've done it. It's just pretty much if you integrate both sides, you get this result straight away.
That's a nice way of looking at the graphical one, I think. It's sensible. Cool.
Okay, and arguably the most important one in this question is v squared equal u squared plus 2as. And how would you get at this result is basically you use the first equation to work out t in terms of u, v, and a, and use another equation which is s equals a half u plus v times t, which again can be seen from a graph because that's just a formula for the area of a trapezium. You can try it in your spare time when you eliminate t in the first equation and then substitute it into the final equation. You arrive at the third equation here.
Sorry. That's, yeah.
Yeah.
Back on.
So has anyone done the first part of the question and get it right?
It's a tricky one, isn't it?
3. I kind of skipped over it.
Yeah.
Really want to do it.
Okay. So what do we know right now? We know that when it's at height 0.5 meter, its goes speed 6 meters per second. What do we know about the speed of the particle when it's at its greatest height? When you throw something at its greatest height, what's the speed when it's reaching its maximum height? It's 0, right?
0.
Because if it's still moving upwards, it's not at its greatest height. So we know that in the first part of the question, we know u equals 6, v equals 0. What else do we know? What's a?
At the peak height? Is that
Just what's a throughout the question? Acceleration.
What's causing it to change its speed as you throw something out?
So what force is causing everything to fall down?
gravity?
So gravity. So a is just g, and that will be 10. And then we have because if you look closely at this equation here, we have 4 different letters, so 4 unknowns, and we already know 3 of them, so we can work out the 4th one. So 0 squared equals 6 squared plus 2 times. But we have to take care here because gravity is acting downwards and we're taking upwards as positive. So a should be minus 10. And rearranging, we'll get s equals 1.8 meters. And combining with the 0.5 meters is really traveled the greatest height above the ground. Above point O would be 1.8 plus 0.5. So let's just look back at this question. We're throwing from point O, and it's traveled up to this point 0.5 meters above point O. And at this point, we know its speed u, and we know its acceleration a. We can then work out its final height using the third Suvat equation. And that's how this kind of question can be approached in the future. 3. So now we're trying to find the time after projection at which the particle returns to O. So the third equation of motion doesn't have time in it, so it's not of much help. But the other equation of motion does have time in it. And so here we can introduce a little trick. When we throw something into the air, it's decelerating due to gravity, right? And then it's accelerating again due to gravity. And this motion is completely symmetric. How much it accelerates is the same as how much it decelerates. So if I throw, ignoring air resistance, if I throw the pen from here, we reach upwards and then drop down, the absolute speed at this point would be the same. So it's just like saying the time taken from this point to the greatest height is the same as the time taken from the greatest height to this point. So, so because of this symmetry, we can use the fact that S equals ut plus 0.5 gt squared. And S is just the distance between the greatest height and point O, which we've worked out before as 1.8. And U is 0 because when you reach the greatest height, your velocity is 0. So we have 0t plus 0.5 times 10 times t squared. And from there, we can work out what it is, which is 0.628, I believe. Any questions?
One thing to remember is that 0.5 doesn't come from the height, that comes from the equation.
Yeah, exactly.
So just remember that. If you're looking at this later thinking, oh, where did that not? So it comes from a half, just written as 0.5 gt squared, yeah. Okay.
So I think just after a little bit of practice, it will just come naturally which equation to use.
Yeah.
And most of the time, it's not unique. Maybe 2 or 3 different equations would work. Maybe just one of them will take a little bit more time.
Okay. A little break. 5 minutes just to refresh the brain, then we'll go on to question 4. Okay. Brilliant. Go out, quick walk. Stretch your legs. Stop yourselves getting tired. Nice. Excellent. It's going to take a little bit of time, isn't it? Getting used to kind of the writing and then changing between the tools, but that's fine. It's no problem. I'm not sure. I mean, once you get good at changing between these things, what's weird about this is it's not an accelerated trackpad, right? So you can't go fast and then you do that a few times and you think, oh no, actually you actually have to go to the physical place. But I think changing on these sort of and getting used to doing the lines, and you've got to go off. So the trick is, right, when you're doing line axes, is not go like there and then try and do it from there, because it will pick up that one. So you draw it that way and then draw this one that way.
Yeah.
And then that's just a quick way. But we'll find this out, won't we? I'm sure there. All right. The sort of interactivity will come more as they get more confident. I don't think you have to worry too much about asking them what they know already, because really don't forget they haven't really been taught anything at all.
Okay.
So it's quite a natural, right, isn't it? But they're trying to just work out as much as they can by just looking.
Obviously, what I'm used to is that I'll
you teach it.
teach them the course content, and they will do the question.
Okay.
Yeah.
That's normal. So this is more like the supervision method where
Exactly.
you get a problem set.
It's quite a big ask.
It's a massive ask.
Yeah.
But we've told them to prepare to just be okay with the fact that you don't get it. Be okay with the fact that you feel like you're drowning at first. But over a period of time, you get used to it. So don't worry about teaching too much of the, as things come up, just introduce them. I see that. Get back in. Go back. It's a danger of letting people out of the room, isn't it? Yeah.
That's right.
Right. So the thing about, I think M1 is that it is the easiest module in terms of how hard the questions are. In pure math, you rely more on problem-solving techniques, and on mechanics is a lot more about knowing the formulas and not be afraid of doing calculations. And once you get to know the formulas, it's really not hard at all in exams. Question 4. 3 coplanar forces of. This is basically telling you, when you have a diagram like this, it's telling you to resolve forces. And normally we resolve forces in 2 different directions. So, why do we know that we need to resolve forces? That's because in a diagram, the forces are in equilibrium. So we know that the total force pulling to the left will be equal to the total force pulling to the right. Horizontally speaking, that is saying that 15 Newton, that's this force here, times cos alpha, that's the total force pulling to the left, will be equal to F times cos 60 degree and plus 2F, and vertically it's saying that 15 times sine alpha will be equal to F sine 60. Especially saying that the forces pulling downwards will be equal in magnitude to the forces pulling upwards. And how to solve this equation as quick as possible is by noting that on the right-hand side of both of these equations, there's a common factor of F. So F times cos 60 plus 2. And cos 60 is just a half, isn't it? So especially equals 5 over 2 F. And what you do now is you divide one by the other. Let's say this equation is equation 1, equation 2. and you divide equation 1, equation 2 by equation 1, you get that tan alpha is equal to sine 60, which is root 3 over 2 over and from this expression you can work out what alpha is just from the calculator.
So that's a good trick there, isn't it? So spotting, what's the thing to spot? Because you could do it a long way around, couldn't you?
Yeah, you could solve it as a simultaneous equation, but in this case, just by noting there's a common factor can speed up the process.
Yeah. So you've got to know that sine over cos is equal to tan for that, which you should know. And if you spot the fact that there is a common factor
Of f.
Yeah, on that side. So there's a little bit of insight there, isn't there, to see that? Yeah, brilliant.
And after working out the value of alpha, all the other steps are just pure algebra.
Yeah.
So let's leave it at that.
4, 5.
Okay, question 5.
So that's quite an easy 6 marks on that previous question, you think? 4? Yeah. Okay, question 5, cool. Did you guys have a crack at number 5?
Yeah.
This diagram on here?
You read 4 as well.
Cool.
So this is an example of velocity time graph. And one of the most important ideas is that area on the graph is equal to the distance traveled, which intuitively makes sense because v on the horizontal axis times t, vt should be s, right? So that's how it should be interpreted. Find the acceleration of the cyclist during the first 10 seconds. Okay, so this is the first point, 1.
Yeah, change the size of it.
And 2. Gradient of the graph is equal to acceleration. So find the acceleration of the cyclist during the first 10 seconds. You see, during the first 10 seconds, the gradient of the line segment is constant. So we can simply divide 5 by 10 to work out the gradient. It's the same with any kind of graph. So
that makes sense to you guys, the gradient, yeah? Okay.
And they'll give you 0.5. And show that the total distance traveled by the cyclist in the 90 seconds of the motion may be expressed as 45v plus 150. That's pretty much just summing up these different shapes. So here we have a triangle, and here we have a rectangle, and rectangle and triangle again. So these should all be pretty straightforward. The only thing might be hard is by noting that v is here. It's not a number. It's an unknown quantity. So we can just substitute in v for all the different quantity, and equal that to 465 meters, which we were told in the questions, and that should give you the expected value of v, which is 7. The last question is a little bit more interesting. The combined mass of the cyclist and the bicycle is 80 kilograms. The cyclist experienced a constant resistance to motion of 20 Newton. So the energy method is pretty much saying that energy cannot be created or destroyed. So energy can only be converted from one form to another. And in this case, when the cyclist is going downhill, it's losing what we call gravitational potential energy, and it's gaining kinetic energy, but at the same time it's losing energy as well because of resistance to motion. So let's take a closer look. So the cycle is originally here, and then after it's going downhill, you'll come to a position here. And because of the change in height of the cyclist, you'll lose GPE. And also there's a resistance to motion of 20 Newton. So the change, this delta sign just means change of GPE equals work done against resistance plus kinetic energy. Also, one reason we can be sure of this equation is because the cyclist assumed to do no work, so it's not trying to accelerate itself. So there's no conversion between the chemical energy stored in the cyclist state to kinetic energy. So this is the only energy conversion happening here. So what's the GPE lost? It will be 80. That's the mass of the cyclist times G, which is 10, times the change in height. We call the change in height H. And it will be equal to the change in kinetic energy plus the distance traveled, which is 7 plus 5 over 2. Do we know how to work out the change in kinetic energy? It's pretty much just because kinetic energy is equal to a half v squared. So the change will just be a half times 80 times 7 squared minus 5 squared and plus this lot. And that will give you H after rearranging the equation. Any questions about? Okay.
Did you know the formula for kinetic energy? K equals half mv squared. I think energy ones, once you get them, they're very easy, but you do need to know kind of what the kinetic energy is, and you need to know the gravitational potential energy. Kind of the formula for that is just MGH. You can Google it, of course, the first time, but GP is just MGH.
Yeah, I'm able to formula.
Yeah, good, well done.
Okay.
Worked it out. Cool.
So coming to question 6.
Mhm.
Yeah. So maybe we should take some time to explain what I meant by work done. So in motion, we have different quantities as affecting motion. Say, so we have force, and we have energy. And obviously, there's an interaction between force and energy. And how that is brought about is that work done, which is the same as energy, is equal to the inner product is the inner product of force and displacement. So what does this statement mean? It means that
Make it a tiny bit bigger.
Huh?
If you make it a tiny bit bigger, it will all fit on the same line. That's it. Yeah. Sorry, is that what you wanted to do?
so what do we mean by inner product? It's just when, for example, you have a particle traveling just vertically upwards, and you have a force pulling it in at an angle, let's say 60 degrees. And the inner product is just the force times the distance, but times again the cosine between them. So there's an angle here. And that's the interesting thing. That's because the cosine of 90 degrees is 0. So if a force is acting perpendicular to the direction of motion, it's not doing any work. And that's something that will be used in later questions. And this is one way to relate work done as a way to relate force and energy. Question 6. A block of mass 25 kilograms is put along horizontal ground by a force of metric. So find the work done by the pulling force. In this case, the force is at an angle 10 degrees with the direction of travel. And it's traveled a distance of 20 meters. So it should just be 50. This is F times 20. This is distance of travel times cos 10. This is the part where we've said it's an inner product. And that will give you the work done. It's just its definition, and you have to remember it. And in this case, we'll work out the work done by the pulling force from question 1. And which is 984.8. And the change of kinetic energy is just the total kinetic energy of the block. So there will be a half times the mass of the block times the speed of the block, which we're trying to work out, and plus work done by resistance. And the resistance is constant and of a magnitude of 30. So it would just be 20 times 30. Rearranging this equation, it will give you the value of V, which is 5.55 sometimes we can deduce certain property of the question just by common sense. For example, if you are pulling something up a slope, the speed at an early time cannot be greater than the speed at a later time, because if the force is constant, it will either go faster and faster, or go faster and faster and reach a constant speed and not go any faster. So we can assume that the final speed is the greatest velocity.
We lost the broadcast for some reason. I'm just carry on. I'll just. Sorry, yeah. 2. What was it? We've got the 9709, 41. It was October 16, wasn't it?
Yeah, 16.
October 16.
What's the channel's name?
Sorry?
What is the channel's name?
This is Z class is the what we've called the channel.
Okay. So that's what we're allowed to be.
Correct. Well, I'll put everything in the you're already in a video call. Oh, take me there. Oh. Oh, so it just lost the screen share. That's all. Okay, fine.
So it's recording the talking bit, but no.
No, just a little bit. It was just for some reason it's entire screen application window. Just a glitch in the matrix. So we'll go for the whole screen, and then we will. Yeah. We'll change quickly. Back on.
Right.
Sorry. Yeah.
So find the greatest power exerted by the 50 Newton force. Here is another formula which you might not have seen before. As power equals F times V. And if you want the greatest power, we just need to find out when V and F is the greatest. And F is always constant, it's 50, right? So it's just 50 times V max. And as I said before, the maximum cannot be greater than 5.55. So it will just be 50 times 5. And that will give you 273 watts. So in the last part of the question is asking you how much time it will take for the block to stop moving. And in this case, we know that right now, because it's inclining at an angle to the horizontal line, it's gaining gravitational potential energy as well as kinetic energy. So we'll have to work out a new equation for our new quantities. So here we again use Newton's second law, 25, which is the mass of the block A. So the left hand side is MA, because the right hand side should be resultant force. So what force do we have on this block? We have 50 cos 10. Again, we have to remember that we're just resolving in the line of motion here. So Newton's second you have to apply it in each direction. So right now we're applying Newton's second law in this direction. Perpendicular, horizontal to the motion. and that will be that minus 30 resistant force minus 25 times G times sine 5, which is the component of gravity acting parallel to the inclined plane. And from this equation, this Newton's second law equation, we can work out the acceleration to be a negative number, minus 0.102. Because there's a deceleration and the initial velocity v equals 5.55, we can work out t. It's just simply v minus v over a, because that's the time it would take to completely get rid of the initial velocity, and that will give you the time to come to a rest. And now that one last
So last question. Okay, let's just have 2 minutes. 2 minute quick break before the last question. Stretch your legs, get your brain ready. There's only one question. It's a fairly long one, so we'll see if we can sort this out. It doesn't appear to be one, but it seems to think that it is. So, no. No, there's a glitch in the matrix.